Okay, so the next thing that we will talk about is how does the convolution operation affect the size of the output feature map? Okay, so imagine I have an input size of n by n. So my input matrix is here, and the filter size I have is k by k. The question is, what is the height and the width of my, excuse me, output feature map? Um, so when we have an n by n input and a k by k filter size, I will be able to move uh, n minus k times to the left, right? So this is my original position, and I have two columns, or rather n minus k columns to my right. And because if I move for ones, I will use one column. So this n minus k columns allows me to move n minus k times to the left. And plus the original position which I begin with, right? So this in total gives me n minus k plus one positions or to the right, I'm sorry, n minus k plus one columns in the output matrix. And similarly, I will have n minus k plus one rows in the output matrix as well. Okay, so what would happen if I want to have um, constant feature map size across the layers? And that means I have to add some padding, right? So I can do zero padding, or I can do other types of padding, but I basically need k minus one rows and k minus one columns. And the typical practice is to use half of the rows on the top, to put half the padding rows on the top and half the padding rows on the bottom of the original input. And similarly, I get half the padding on the right and half the paddings on the left. So that means k minus 2 over k minus 1 over 2 better be a integer. In other words, k is an odd number, right? So this is also another reason why we typically use filters with odd number sizes. So we'll look at the padding and what kind of padding we can use. I think the most commonly used padding is the zero padding. So here the yellow matrix is my original input, and the green part, sorry, the blue part is my padding. And zero padding, I think, is the most straightforward and the most commonly used. But you could do other paddings as well, such as mirror or duplicate, right? These are hyperparameters you could set in the deep learning framework. In mirror padding, basically, I want to take the value that is symmetric with respect to the boundary of the image, right? So I'm going to define the boundary of the original input as these grids or these pixels. And for the green pixels, for the blue pixels, I want to find the position that is symmetric with respect to the border. So 20, this position, the symmetric position, I'm going to find the symmetric position with respect to this straight line, and that is this 24 here. So I'm going to copy this value over. So that's like mirroring the values with respect to the boundary of the input matrix. And for this position, I will find the mirror position, which is here, and copy its value, right? For this position, the closest point is this one, so the mirror position is really this central pixel, and we'll copy this value over, okay? And alternatively, we could use duplicate or nearest neighbor padding, which is for any pixel in the padding, we will find the nearest neighbor in the original image and copy that value, right? So for this value 5, the closest pixel in the original input is here, and I will copy that over. And take any value Here, for example, the closest pixel is the one above it. So I will copy the value 23 over to this padding position. Um, the motivation to use other types of padding is that um, in the zero padding case, let's say you have 3 by 3 filters, and you put a filter uh, in this position or in this position, right, there will be a lot of zeros in your input. So the input values tends to be relatively, so the input values are close to zero or mostly zero, and the output values will be relatively small compared to other positions. Let's say this position, most of the values are non-zero, so it's possible that you get a large value as compared to those near the border. So in the mirror padding and duplicate padding case, it's unlikely to have like really low values near the border. But in practice, this does not seem to be a major concern, and zero padding is still the most commonly used style of padding in convolutional neural nets. Another possible thing that you can tweak about convolutional operations is known as stride. Basically, stride is how many pixels you move at the same time. Okay, so if you set stride to 2, then you're moving 1 pixel at a time, either to the right or down, right? So this is basically the most common case where if I move by 1 pixel to the right, I get to this position, and then I can move another pixel to the right. Then after that, I will move one down, and so on and so forth. But if I set stride to 2, then I will not have this position. I'll move directly to the rightmost column in this diagram. And when I move down, same as principle applies. So I move down by 2 rows at a time. So this is when I set stride to 2. Another possible design parameter is known as dilation. Okay, so dilation basically means where do you apply your filter values. Okay, so for dilation being for dilation, if dilation is set to 1, this is the most common case. All right, so you have the 9 by 9, sorry, 3 by 3 filter matrix closely knit together, adjacent to each other. But if I set dilation to 2, there will be 1 row and 1 column of space between these values. So I will apply these pixel values, these filter weights at different locations, and the locations will be further apart. And I will do the multiplication here with these corresponding pixels, and then take their sum, and can further set dilation to 3, and so on and so forth, right? So when I set dilation to 2, these a 3 by 3 kernel filter or convolution kernel basically covers a 5 by 5 space. If I set dilation to 3, they will cover a 7 by 7 space. So here is the equation for computing the output feature map. This is particular to PyTorch, so it's very particular, and other frameworks may differ. But in PyTorch, basically, you could specify a padding value for height and width separately, though we tend to use the same value, but you could definitely change that, right? So by default, PyTorch applies the same padding on the top and the bottom, and to the left and to the right. So we will have to multiply the specified padding value. So if your padding is 1, that means you add 1 row and 1 row on top and 1 row at the bottom. So this is my original size, my original height. This is the amount of padding I add on top and bottom. And so this is kind of the new n, right? The new input feature map size. And remember my equation is n minus k plus 1, where n minus k is how many times can I move either to the right or down. Okay, so I have just found n that's here, and my k is basically this value, right? So this basically calculates the effect kernel size. Okay, so if I don't have any kernel, then it's just simply k. If I set dilation to 2 or 3, basically I get this is the way I can compute the new kernel size, right? Remember, for a 3 by 3 kernel, if I set dilation to 2, that gives me effectively a 5 by 5 kernel. If I set dilation to 3, that effectively gives me a 7 by 7 kernel. So this is the equation for computing the effect kernel size when I set dilation to a number larger than 1. All right. And I also talk about stride. So stride is by how many pixels you move, right? So this is how many pixels you have, and we have to divide this number by stride. Oops. We'll divide it by stride to know like how many times can I move. And there is also the original position, so that you have to add 1 to that. And remember that we cannot have a half of a pixel or a fractional size of a feature map. So I cannot round up. I have to round down. Okay, so I'm going to use the floor operation here because I can throw away some positions, but I cannot like make new pixels out of thin air, right? So I have to round down. So this equation gives you the output size of a feature map going through a particular convolution operation which are specified by the amount of padding, by the stride and the dilation, as well as the kernel size. So the next important idea that we want to talk about is known as the receptive field. Okay, the receptive field is like how many pixels does one pixel in the output sees, but rather how much information has been aggregated into this particular pixel. All right, so if you look at this pixel, after one layer of convolution, you may ask, like, how much information does this pixel aggregate in the original input? So my input is n by n, my filter size is k by k, and obviously there are k by k pixels here that get involved in the computation of a single pixel in the output. Okay, so in other words, I can say that one pixel in the next layer sees k by k pixels from the previous layer. Okay. And if I do one more layer, I might ask, how many pixels, if I have an output of k by k, if my output is of size k by k, then how many pixels in the layer before that have contributed to the calculation of these k by k in the output, right? So how do I calculate that? Now, assuming that my kernel size is k, and my original input size is n, and these n by n contributed to the output size of k by k, then I can create the equation that n minus k plus 1 is equal to k. Right? This says if my input size is n, and I have a k by k filter, the output size will be n minus k plus 1, and I know that the output size is also k, all right, is also k by k, so I can solve for n. And it's easy to see that n is equal to 2k minus 1. right? So K by K pixels in the next layer basically aggregate information from 2K minus 1 times 2K minus 1 pixels in the previous layer. Now we can really put those things together, right? So from the first layer, we go from in the first layer, we go from 2K minus 1 to K, and in the second layer, we go from K to 1 to a single pixel. In other words, if I have a two-layer convolutional network, one pixel in the output sees or aggregates information from a total of 2K minus 1 by 2K minus 1 pixels. And this is known as excuse the typo, receptive field corresponding to the pixel. All right. So what about 3 layers? Can I do that? All right. So typically, if this were a in-person lecture, I would ask you to scan the barcode and put in the answers and input the answers, and and we can see the votes in the class. But since this is a pre-recorded video lecture, I'm going to skip that step. And what I'm going to say is, I'm just going to show you the calculation, right? So going from layer L plus 1 to layer L, so going between these 2 layers, right? What I did, my calculation was, this is my, if n is my unknown, and if my output size is, I know it to be k, what is n? And my calculation is like it's equal to 2k minus 1, right? So basically, I will apply the same methodology, treating n as the unknown, and after the convolution operation, the output size is 2k minus 1. So the question is, what is this size here? And we can easily solve for n, and we can see n is 3k minus 2, right? So it's basically a linear function in k in kernel size, given that we have not applied any stride or we have not used dilation. So that's the idea of receptive field in convolutional network. Okay, so what happens when dilation and stride are not set to 1 and padding is not set to 0? How would we compute the receptive field then? Right? I think the simple answer lies in lies in using the equation for computing the output size, right? So basically, we will take H in and W in and treat these as unknowns. The padding value, dilation value, and stride values are known, and the output size is also known. And then we will be able to solve for the unknown, and then we will find the receptive field that way, right? So I think that's a simple equation solving that I expect most of you to be able to do. There is this interesting relation between the resolution of the input image versus the receptive field. So imagine if you have a very high resolution image and a relatively small receptive field. That means each of the pixel in your output sees really a small portion of the original image. And if you see something like that, will you be able to tell what kind of object or what kind of animal this is? I think it will be very difficult even for the smartest human being, right? Because there simply isn't enough information. So if you wanted to recognize the image or as in object recognition, or if you wanted to classify the pixels into like what kind of animal, this is typically known as the semantic segmentation task. That would be difficult to do because we simply do not have enough information to make these decisions. Okay, so that is obviously not great. What if you have a high resolution image and a large receptive field? Okay, so that is good because one pixel will be able to see information from pixels that are far away, and we will be able to make decisions such as to recognize the object in the image as a dog, or to classify pixels as, uh, are these pixels are belonging to the dog, and outside these red lines, those pixels like don't belong to the dog. Um, However, to process a high resolution image and to reach a large receptive field can have high computational cost, as we saw that the receptive field can increase linearly with the number of layers. So to have a large receptive field, sometimes you need many layers, and that also adds to the computational cost. Okay, so this is necessary sometimes if you wanted to make very fine-grained decisions, such as pixel level classification, and you wanted to make sure to very uh, exactly find the boundary, very precisely locate the boundary between the dog and the background. And in those cases, you often need a high resolution image. And we have ways to create large receptive fields without increasing computational cost too much. But typically, you need a little bit of computational cost. However, if you're only making some coarse grain decisions, such as image recognition, where you're trying to classify the entire image into one type of object, such as dog or cat or bird or fish, then you don't need a very high resolution image to do that, right? So the economic way is perhaps to use a relatively low resolution image and coupled with a sufficient but relatively small receptive field that allows you to see the entire image, but that does not create a lot of computational cost. And this will be the middle case, which is, economic and efficient for coarse grained decisions such as image recognition. Okay, so if you look at literature on like other types of computer vision tasks, such as semantic segmentation, they will talk more on this issue. And here we're just only going to give you a brief discussion, since this is really an introductory course, and we wouldn't dive into the details of the more advanced computer vision tasks. All right. So receptive field and resolution. Um, a common uh, in neural networks for image recognition, a common thing to do is to gradually lower the resolution of the feature maps. Okay. So this allows us to increase the receptive field and the without necessarily incurring a lot of computational cost. The input resolution could be a relatively high or maybe medium by today's standards. And throughout the networks, we will apply some downsampling operations. And these operations have the effect of increasing receptive fields and reduce the spatial resolution, so which potentially saves some computation.